Okay, so we're going to start our standard sessions for the day. The first speaker up is going to be Saksham and Rachit and company. They've been, they're old friends. They've been here a few times, and they're going to talk about a new congestion control architecture that they've been working on.
Hi, my name is Saksham Agarwal. I'm a PhD student at Cornell University. And today, I want to talk about congestion control, but for a new kind of congestion within the hosts or host congestion. In particular, I want to tell you a bit about how host congestion forces us to revisit the problem of congestion control and what we have learned so far in terms of understanding host congestion and resolving host congestion. All right, let's jump right in. The conventional wisdom in our community is that congestion happens primarily in the network core, that is, at network switches. For instance, due to oversubscribed topologies, in-cast traffic patterns, poor load balancing, etc. However, recent studies from large-scale production clusters like Microsoft, Google, Alibaba, etc., have demonstrated a new phenomenon: emergence of congestion within the end hosts, especially adoption of multi-hundred gigabit access link bandwidths, coupled with relatively stagnant technology trends for resources within the hosts. For instance, cache sizes, memory bandwidths, memory access latencies, etc., has led to the emergence of host congestion. For instance, a recent hotnet study demonstrated the evidence of host congestion in Google's production cluster. The figure here shows link access bandwidth utilization on the x-axis and the measured packet drop rates at the end host on the y-axis. The colors on the scatter plot denote the density of the sample points, with purple colors indicating larger fraction of samples. This study showed that even with state-of-the-art congestion control protocol and state-of-the-art user space network stack, the hosts in Google production clusters observe significant packet drops even when the link access bandwidth was far from saturation. We're also able to reproduce this host congestion phenomenon using an open source network stack and congestion control protocol. In fact, today I'm going to provide a live demonstration of these results showcasing the impact of host congestion using a setup consisting of a single sender and a single receiver host connected directly to a switch using 100 Gbps access link bandwidths. This setup ensures that there is no possibility of network congestion because there is no incast or oversubscription in this topology. I'm using the Linux network stack with DCTCP as the congestion control protocol. I'll show results for a multi-tenant scenario with two network applications running concurrently, a throughput-sensitive application and a latency-sensitive application. I'm using standard benchmarking tools, iPerf and Netperf respectively for each kind of app. And I have all TCP optimizations like TSO, GRO, and ARFS enabled. To introduce host congestion, I'll use a memory-intensive application running locally at the receiver along with the network apps. This memory-intensive application will generate a steady stream of memory reads and writes. I'm currently using MLC, a standard benchmarking app for such memory-intensive workloads, but we have observed similar behavior with other applications like Redis, for example. But today I'll be using MLC just for the sake of better explicability of results. Okay. The dashboard here will display the metrics in real time as I'll run the experiments on my local testbed at Cornell. Okay, so let's go ahead and launch the throughput sensitive application and the latency sensitive application. I've provisioned enough CPU cores for each of the applications so as to ensure that there are no CPU bottlenecks in the system. In the default no congestion scenario, we observe that the throughput sensitive application saturates our access link bandwidth of 100 Gbps. The latency sensitive application achieves tail latencies around 100 microseconds, even at very high tails like P99.9. Unexpectedly, since there is no congestion right now, the drop rates are near zero. I will now introduce host congestion by running an instance of the memory intensive application. This will lead to significant performance degradation for network apps. I'll tell you why and how this degradation happens in a bit, but let me first showcase its impact. Okay, so we see the network throughput degrading by up to 55%. The tail latency is inflating by multiple orders of magnitude. And such large inflation in tail latencies is primarily because of retransmissions and timeouts caused by packet drops. Host congestion here is leading to a steady stream of high drop rates of around 0.3%. Our SIGCOMM paper provides more details on the workloads used and additional results demonstrating the application level impact on host congestion. But I would like to note that the host congestion is a problem that can happen today, not that it will necessarily happen on all hosts and workloads. This is quite analogous to the incast problem in data centers, like where incast doesn't necessarily happen for all workloads. But I think it is important for the community to understand the severity of the problem and start addressing it. We have open sourced the workloads, experimental setup, and the infrastructure needed to reproduce our results so that the community can start exploring the problem of host congestion. Please check out a GitHub repo for the same. To understand host congestion, we need to understand the host interconnect. Today's host interconnect has three main components. First, the processor interconnect is used by the CPUs to exchange information amongst themselves and send read or write requests to DRAM. The peripheral interconnect is used by the NICs to send read or write requests to CPU and to DRAM. The memory interconnect, or the memory controller, intercepts the read or write requests from NICs and CPU cores and executes them on DRAM. Importantly, the peripheral interconnect connects to the processor and memory interconnect using an integrated I/O controller known as the IIO. Now, the host interconnect has two interesting properties. First, the hardware guarantees lossless data transfer using a hop-by-hop credit-based mechanism. In particular, each of the processor, memory, and the peripheral interconnect implements a credit-based flow control mechanism to ensure losslessness. And as we will see, the problem of host congestion happens due to poor interaction between these three flow control loops. Second, the host interconnect is shared by both the network application and the host local application. Importantly, the network applications use congestion control, but the host local applications do not. I cannot describe what I mean by host congestion. Like most real-world network fabrics, even the host interconnect is also oversubscribed. For instance, traffic from host local applications and the network applications can contend for the memory interconnect bandwidth, leading to congestion at the memory controller. And since the host interconnect is lossless, this congestion results in a back pressure all the way back up to the NIC. And this leads to packets being queued and eventually getting dropped at the NIC. And this problem of host congestion is likely to worsen over time. the amount of bandwidth for peripheral traffic, for example, from NICs and other PCI attached accelerators like GPUs, is increasing at a much faster rate than the memory bandwidth. The plot here shows the amount of memory bandwidth over subscription due to the peripheral traffic over time. We see that for the latest available Intel and AMD processors in 2023, the total amount of PCI bandwidth has even exceeded the available memory bandwidth. In addition to the peripheral traffic, there's also a significant amount of memory bandwidth over subscription due to host local traffic generated by the CPU cores. And historically, the amount of oversubscription due to the host local traffic has remained and will continue to remain stagnant over time. But the overall memory bandwidth oversubscription is increasing and worsening the problem of host congestion. Our work takes the first step towards alleviating the problem of host congestion. Host congestion requires us to rethink the congestion control architecture along multiple dimensions. First, we should rethink the congestion signals used to capture host congestion. The typical view of the network is that network begins and ends at the NICs. Commodity NICs today do not even provide visibility into the queue occupancy at the NIC buffers. And traditionally, congestion signals such as switch buffer occupancies, queuing delays, or packet drops have usually sufficed to capture the time, location, and reason for network fabric congestion. Host congestion, however, is a result of queuing at resources like the memory controller, which is typically considered outside of the network by existing CC protocols. Furthermore, the interaction between the lossless host interconnect and the lossy network fabric interconnect further complicates the challenge of getting the right congestion signal. For instance, classical CC literature assumes that the packet queuing or drops happen at the congestion point. In contrast, host congestion results in packets being queued and dropped away from the actual congestion point. For instance, the packets are being queued at the NIC buffers, and congestion is happening at the memory controller. Indeed, traditional signals like switch buffer occupancies or packet drops fail to capture the precise time, location, and reason for host congestion. Host congestion will also requires us to rethink the congestion response. This is because of two reasons. The first is that, unlike network traffic, the host local traffic does not employ congestion control mechanisms. Classical CC literature that assume that all competing traffic must adhere to the congestion control protocol can lead to starvation for the network traffic. This is because in the presence of host congestion, NIC buffers can build up, leading to an increase in delay or packet drops for the network traffic, resulting in my transport protocols reducing their sending rate for the network traffic. However, the host local applications today employ a form of flow control mechanisms. That is, their CPU cores typically keep a certain amount of in-flight requests to memory at any point of time. The host local applications today continue to keep the same number of in-flight requests to memory, independent of the presence of host congestion. The second reason we must rethink congestion response is that the host local traffic is much closer to the point of congestion and can change dramatically at sub-microsecond timescales. Thus, the classical congestion control protocols that operate at network RTT granularity can perform far from optimal in the regime of host congestion. HostCC is a new CC architecture that handles both host congestion and network fabric congestion. The key architectural idea in HostCC is a sub-RTT granularity host local congestion response. This idea builds upon a conceptual view of congestion control. It allocates resources among the competing entities. HostCC sub-RTT granularity host local congestion response allocates the host resources between the network traffic and the host local traffic. At the sender, HostCC uses the host local congestion response to ensure that the network traffic is not starved even at sub-RTT granularity. At the receiver, hostcc uses the host local congestion response to minimize queuing and packet drops at the host. It modulates the host resources allocated to the network traffic at sub-RTT granularity to ensure that the NIC queues are drained at the same rate at which the network traffic arrives at the NIC. Let me now provide some of the most interesting design details in hostcc architecture. First, in addition to congestion signals from within the network fabric, hostcc generates host congestion signals at the host interconnect at sub-microsecond timescales. These host congestion signals enable hostcc to precisely capture the time, location, and reason for host congestion. Specifically, hostcc uses IO buffer occupancy as the host congestion signal currently. IO occupancy can be measured by reading a single hardware register typically available in commodity hardware, allowing hostcc to work without any hardware modifications. I will now quickly demonstrate the efficacy of using IO occupancy as a host congestion signal. In the default no congestion scenario, where the network throughput is close to 100 Gbps and we have low tail latencies and no drop rates, the IO occupancy is steadily hovering around 65 cache lines. However, when we introduce host congestion, let's give our host local application a few seconds to load up. We see host congestion has started with degradation in throughput and increase in drop rates and latencies. The IO occupancy also increased in correlation with host congestion, with the new IO occupancy values closer to around 90 cache lines. This is in correspondence, as I discussed a couple of slides ago, that IO occupancy increases due to back pressure from the memory controller in the presence of host congestion. IO occupancy is measurable on a commodity servers at sub-microsecond timescales. This is evident from the plot, which shows the CDF of the latency of measuring the IO occupancy value by reading the corresponding hardware registers. On our commodity servers, almost all measurements took less than around 600 nanoseconds. And since it was hard to visualize the microsecond scale behavior of IO occupancy on the real-time dashboard, let me quickly also show you the IO occupancy behavior captured for a much smaller time horizon for the same experiments as in the dashboard over a 1 millisecond time horizon. We can clearly see under no host congestion scenario, the IO occupancy hovers around 65 cache lines. And in the presence of host congestion, it increases at sub-microsecond granularity due to the back pressure until it saturates at a maximum observed value of around 92 cache lines. hostcc uses its host local congestion signals to perform its host local resource allocation at sub-microsecond granularity. Current hostcc implementation enables the operators to specify the desired resource allocation policies for host local and network traffic resource allocation, and employs tools available on commodity hardware that rely on back pressure-based mechanisms to perform this host resource allocation. For instance, the memory bandwidth allocation tool, or the MBA, available on today's Intel servers provide a simple multi-level back pressure mechanism to modulate the host local traffic using updates on a single hardware registers. It currently takes as input one of the 10 allocation levels via such register writes and provides an increasing level of back pressure to the memory bandwidth generated by the CPU cores. This allows hostcc to perform its host local congestion response without any modifications to the applications or the hardware. And similar back pressure based tools with similar interfaces also exist on other platforms like AMD. Note that host CC architecture does not dictate precise resource allocation policy. Just like different network resource allocation mechanisms can use different allocation policies like maximum fairness, prioritization, etc. We envision host CC to embody various host resource allocation policies and respective implementations. The current host CC implementation assumes that the policy periodically computes a target network bandwidth and feeds it as an input to host CC. The congestion response mechanism operates on a per packet basis and makes a decision whether to increase or decrease the resource allocation to both the network and the host local traffic. Now, to demonstrate that host CC can enforce desired resource allocation policy, I will rerun the same host congestion experiment. Turning on host congestion. Host congestion is active. Let's enable host CC using its host local congestion response, using a default target rate of 80 Gbps. We see that as we turned on host CC using its host local resource allocation, the network throughput quickly converged close to the desired target rate of 80 Gbps. Now let's try to vary the target rate. Let's say reducing it to say 60 Gbps. So as soon as we varied the target rate, the host CC ensured that the network throughput quickly converged to close to the new target rate value of 60 Gbps. However, we also see that our tail latencies are still large, a couple of magnitudes larger than the no host congestion scenario. And the packet drop rates are also reasonably high, close to around 0.1%. This is happening because the host local resource allocation ensures that the available host interconnect capacity matches the target rate, but the network resource allocation fails to promptly converge the network sending rate to the available host interconnect capacity. And this is addressed using the third design idea of host CC. Host CC uses both host and network congestion signals to perform efficient network resource allocation at RTT timescales. The key insight is that the sending rate for network traffic must be computed based on the bottleneck capacity, not just within the network, but also at the host interconnect. Host CC can be integrated with any network CC protocol. The only difference is that the protocol will now use both host and network congestion signals. I'll now illustrate an example scenario of using ECN-based network CC protocols. Existing ECN-based protocols react to network fabric congestion by marking reserved bits in the IP header of arriving packets based on the switch buffer occupancy. Whenever the occupancy exceeds a certain ECN threshold, we mark these bits. And this marking is done independently for each switch along the network path. The state of the congestion, that is the marking of these ECN bits, is echoed back to the sender, where the network sending rate is adjusted by the congestion control protocol. I will now show how host congestion signals can be echoed using these ECN-based CC protocols. Similar to ECN markings done at the switches, the host also performs ECN markings, but using host congestion signals, the IO occupancy. Whenever IO occupancy is greater than a certain threshold, the corresponding bits in the IP headers are updated. This process requires minimal modifications to the host IP stack. The transport layer echoes back the ECN signals and the CC reacts to them, independent of the source of markings, that is whether they were generated at the switches or at the end hosts. Therefore, no changes are required in the existing CC protocols, and the sending rate converges to the minimum available network and the host interconnect capacity. Now, although the current HostCC implementation uses ECN-based signals, it's just an example, and HostCC architecture allows incorporating additional signals. For instance, we discuss in our paper some simple extensions to generate delay-based host congestion signals, which could potentially be used in conjunction with delay-based network CC protocols. Although while commodity hardware does not provide NIC buffer occupancy, it would also be interesting to explore whether HostCC can use that as a congestion signal for network resource allocation whenever enabled by the hardware. Let me now show you how HostCC performance fares using the current implementation. As we can see, host congestion is turned on right now with low throughput, high latency, and high packet drop rates. Let's turn on HostCC using all its design ideas together. So I've set the target rate again to be a default value of 80 Gbps. As we see, HostCC quickly converges the network throughput values close to the target rate of 80 Gbps, and also allowing the latency for the latency sensitive app to be low, close to the no congestion scenario, and packet drop rates are near zero. Let's vary the target rate, again reducing it to the 60 Gbps scenario. The network throughput quickly converges to the new target rate of 60 Gbps. And using all the design ideas together, HostCC ensures that while achieving the desired target rate, the latencies remain low, and the drop rates are also low. We can see from the I occupancy, as soon as HostCC were turned on, the I occupancy values are reflecting that there is no host congestion happening when HostCC is turned on. This slide shows the HostCC benefits under host congestion at a glance. HostCC achieves high network utilization and low tail latencies under host congestion regimes. This is enabled by HostCC significantly reducing the queuing and packet drop rates at the host. HostCC's host local congestion response also enables enforcing desired host resource allocation policies. For example, we clearly see that network traffic achieves increasing throughput with increasing target bandwidth for the network traffic, which is specified by the user. And further, HostCC maintains these benefits even when there is network congestion along with host congestion. To increase the degree of network congestion, we varied the degree of incast in the network. For incast workload, we use two senders and a receiver directly connected to a switch. And we vary the degree of incast by varying the total number of active concurrent flows in the network. First, we observe that in the absence of host congestion and in presence of just network fabric congestion, HostCC performance is near identical to the network CC performance, indicating that HostCC has minimal overheads in the absence of host congestion. In the presence of both host and network fabric congestion, however, although the network CC performance without HostCC suffers from reduced throughput and high packet drop rates, but HostCC provides significant benefits. Using all of its three core ideas together, it collects the host local congestion signals at sub-microsecond timescales and is able to modulate the host resources allocated to the network traffic so that the network traffic can achieve the desired network bandwidth. And it also incurs minimal drop rates by ensuring that the network CC converges to a rate that matches the available network and host resources. This experiment therefore demonstrates that host CC interpolates pretty well with the network CC in the presence of both host and network congestion. Our paper provides more details on host CC benefits by doing a deeper dive into the host CC's behavior at a microsecond scale level. So please feel free to check it out if you're interested. Okay, so host CC is only the first step in understanding and alleviating host congestion. And while building host CC, we have learned a lot. And I'll quickly summarize the two most important learnings while outlining a couple of interesting future research avenues based on our experience building host CC. First, the existing tools for host local resource allocation were not designed to operate at fine-grained timescales. So while writing a typical hardware register takes less than 1 microsecond, writing to the register that enables modulating the memory bandwidth allocation on our commodity servers takes around 22 microseconds. And this necessitates a coarse-grained response. That is, each successive resource allocation level results in large jumps in applied back pressure. We need more support from the hardware to perform a finer-grained resource allocation while still at sub-RTT granularity. Secondly, it would be interesting to explore the usefulness of new emerging technologies like CXL and RDMA in resolving host congestion. Our exploration so far suggests that while useful, these technologies may not resolve the host congestion problem by themselves. For example, the emerging peripheral interconnect like CXL can help reduce the NIC to IO latency, but it does not alleviate the IO to memory controller latency. The key challenge in resolving host congestion. And similarly, RDMA, it can alleviate the memory bandwidth congestion by avoiding data copies, but still it does not eliminate host congestion. We believe much more work is needed to exploit these technologies to resolve the host congestion problem. To summarize, the emerging problem of host congestion presents a new opportunity for our community to explore intriguing questions at the boundaries of networking, OS, and architecture. And host CC is only the first step. It's a new CC architecture that handles both host and network fabric congestion, with the key idea of using sub-RTT granularity host local congestion response, along with an RTT level network congestion response. We have realized host CC within the Linux network stack without any modifications in applications, host hardware, or the network hardware. And we have open sourced host CC code and all the required workloads to reproduce our results. Thank you.
Very good work, thank you. I'm glad that you're noticing that host-based congestion is a problem. It is far more generic a problem than just in the data center. We see it on laptops, and we see it in just about any device connected to wireless technologies today. But the core thing that I wanted to ask merely is, what version of TCP are you using? Because its response to packet drop is Reno, and I did not see that level of drop. Everything was very smooth. There was a bug in DCTCP until about 2016 where it had no response to drop at all. So I just want to make sure you're using a current kernel.
Yes.
Okay.
Yes. So we can you hear me? Yes. So we do see this problem with this latest. We have tested host congestion problem with kernel 6.0.
Oh, good. Okay. Well, there's a bunch of new CCs like Prague, etc., that are worth playing with, as well as BBR. Anyway, good work. Thank you.
Hi, question from me. So in your experiments, you're using iPerf, right? And you're looking at like very high sustained throughput. But what if you had, let's say, a large number of clients, and each one was sending fairly small amounts of data, in the orders of megabytes, and together they overwhelm the host, right, in terms of consuming the PCIe or memory bandwidth? How does congestion control react to, what's the speed of the reaction? Would it benefit in that situation?
Right. So assuming like there are multiple clients which are doing a megabyte worth of transfers, still for the duration of the time when they're sending this megabyte worth of transfers, the total
utilization without host congestion can still be close to 100 Gbps, and during that time, the throughput will reduce and we'll see packet drops without host CC. And if we calculate with 100 Gbps transmission rate, doing 1 megabyte of transfer still requires hundreds of microseconds worth of transmission time. And OCC, based on its sub-RTT granularity congestion response, can quickly alleviate the host congestion problem even for this scenario that you talked about. Did that?
Yeah, so I'll expand on that question a little bit, right? So this is your ECN. I think what you're asking is the classic ECN type problem. You have tens of thousands of flows. Who do you assign the problem to? Because yeah,
gigs, that's very easy, right?
yeah, the moment you said 10 meg, I think that's not the answer to the question. But he's looking at few kilobytes, thousands of flows. Who do you stop?
I see. Okay. So yes, so ECN marking is happening independently for each flow. So on the host IP stack, what is happening is for each received datagram, I'll do the ECN markings, and independently for each flow, whichever flow receives the ECN marking, it's gonna do rate allocation. So the short answer is all flows will reduce their rates in a fair manner. Basically, the ones receiving the ECN.
Yeah, thank you.
So from a networking perspective, you're doing that because you've got a single path. But looking at the code, it seems like it's very specific to Intel Skylake and one process. So what do you see about generalizing that to being able to monitor multiple processes and figuring out which one is causing the problem?
Just want to make sure you're talking about multiple processes or multiple processors.
Processes, yeah. So it's basically generalizing the problem a bit to more than just one flow and one process that's causing the host congestion, but it's processes that are coming in and out and multiple flows like David was talking about.
Right. Okay. So the current implementation is monitoring host congestion, which can be happened by like any processors, like for example, the host congestion signal, the IO occupancy, which I talked about, it indicates host congestion, whether it's happening based on any number of like CPU cores running concurrently. So it's not limited. So we are not monitoring host congestion on a per process basis. And regarding the Intel Skylake thing, yes, I am currently looking to generalize the implementation for other architectures like AMD as well, using similar techniques as in the HostCC implementation.
One last quick question.
Sure. Thank you for the talk. This question is more about the future work or like continuation of your work. So you mentioned that the interconnects have a point-to-point credit-based flow control. Like the interconnects can also have congestion outside the host, say on the PCIe switch or on the end device, for example, a CXL device, which is shared across multiple hosts. So what would you think are some of the options apart from like say explicit hardware support that would help congestion awareness in these scenarios?
That's a great question. It's something which I'm also starting to look at. Okay, so here's my view. So what this whole host congestion project is telling us that we should rethink the mental endpoint of the network. Just like you pointed out with all these CXL devices, I could have these another points of congestion within the host. So there'll be this another sort of mini network within our host. And so I think ideally what should happen is that for each possible point of congestion, there should be some signaling, like some host congestion signaling mechanism. For example, just like I talked about this IO buffer occupancy just for one point of congestion within my data path. If possible, if supported by the future hardware, I would also like to have the occupancy of different, say, PCI switches or different memory controllers near the CXL attached memory devices, for example, to provide me some sort of information about the congestion at different hops. And
So I'm going to interject and say this is going to be a long conversation, and And we are out of time. And by the way, I think what you just suggested, Saksham, won't actually work because you have to do per thread, per path, per flow, per VC tracking, which is not going to be the easiest thing to do. And you're going to not even be able to get which congestion applies to you. Like you don't want to be told your PCI switch is congested, therefore you should slow down, but you weren't actually going to use that switch, right? Because you may have multiple paths on the switch as well. So this is a long conversation. I see there's a... okay, yes. Stephen is saying that you should add container, VM, and a whole bunch of other constructs on top of it, and it'll be very hard to track. But this is obviously a very real problem. And there's a lot of interest, so maybe you should also start a mailing list, and people will join that. But we are going to go on to our next talk.